Good morning, good evening, and good night, depending on where you are in the world, and welcome to part one of this week's EETimes University course designed for next-generation automotive lighting requirements, brought to you by EETimes on Semiconductor and broadcast by AspenCore. I'm Patrick Mannion, and I'll be a moderator. We have just a few announcements before we begin, however. The slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can participate in the Q&A session by asking questions at any time during this webinar. Just type your question on the Q&A text area located to the right of the presentation window, and then click the Submit button. At this time, we do recommend you disable your pop-up blockers. At the end of today's session, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of the console. If you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer some one-on-one assistance. So now on to part one of this week's course, Introduction to Automotive Lighting. Our lecturer this week and all week will be Paul Pickering. Paul is Senior Analyst at IHS Markit, where he's been a Senior Analyst for a couple of months now, covering developments in the industrial semiconductor market. He has over 35 years of experience in engineering and marketing, including stints in automotive electronics, precision analog, power semiconductors, flight simulation, and robotics. So it is a great pleasure. I now turn this presentation over to Paul. Paul, take it away.
Thank you, Patrick. The couple of months thing may scare you, but more importantly, I've been working on these products for many years. So today we are going to talk about the big improvements and the rapid pace of change in automotive lighting over actually what's been a very long time now. This is a description of the course. As Patrick said, it will be in three parts. First part today, then tomorrow, and the day after. Today, we are going to talk about some of the basic fundamental definitions of automotive lighting, what's important, how we determine what color is what, some of the standards that pertain to this field, and some of the fundamental definitions about lighting. And then we'll talk a little bit about fundamental lighting technologies. As you're all very well aware, I'm sure, the lighting has been on cars for a very long time, and different technologies have come and gone over the years, and so we'll talk about some of those. And then finally, we'll start zeroing in a little bit on LED technology, light-emitting diode, which is the only semiconductor lighting technology that we'll be talking about. And as we will see, that has fundamental advantages over other lighting sources, and so it's slowly taking over all lighting functions in the vehicle. And then tomorrow, we will carry on talking about LED lighting in a little bit more detail, look at system architectures. Finally, on the third day, we'll do a deep dive into LED lighting itself, some of the key specs for an LED, some of the control schemes that are being used, failure mechanisms, and so on. And then finally, we'll conclude with a look at what's next. It's not a field that's standing still, so things are moving quickly, and there are even while LEDs are being slowly introduced into every aspect of automobile operation, there are the next generation technologies on the drawing board, and we will be talking about those. Okay, so let's get going. So as you can see here, automotive lighting has been around for a very long time. Actually, it's been around since the 1880s, which is going on 130 years. And even before we had lights using electricity, we had candles back in the horse-drawn carriage days, which were used, to illuminate the way and identify highwaymen and outlaws and anybody lying in wait. We don't have highwaymen anymore. We'd like to think that is due to the prevalence of electric lighting, but I'm not taking any bets on that. So as you can see, that the pace of innovation has been fairly consistent over the last 130 years, but with an increase over the last, since about 1990. You can see here some of the notable developments in automotive lighting over the last century. First use of headlamps, in fact, weren't even electric at all. They were acetylene or oil lamps in the 1880s. Electric headlamps came in at the beginning of the 20th century. And then you can see here, as we go on, we have differences in technology. We went from incandescent to halogen to high intensity discharge. We have various other associated functions such as mandatory headlamp leveling, steerable low beam headlights, and so on. And then finally in 2007, we have item 15 here, which is the first low beam LED headlamps were introduced. And those have now starting to appear in all corners of the world and in all vehicles. Of course, typically these things start out with high-end cars and then migrate down through the product range. In general, new developments have started first in Europe and then later in the US. And on day 2, we will be looking at a state-of-the-art front headlamp system for an Audi vehicle and examining that in some detail, just so we can see what types of functions are now available in the market in terms of LED lighting. Of course, because lighting is a very important feature, there are a number of government regulations and standards that pertain to these. Federal Motor Vehicle Safety Standards, FMVSS, Regulation 108, controls automotive lighting in the US and has a Canadian equivalent, CMVSS 108. These types of regulations cover lighting, the allowable colors, and so on, and don't just cover automotive lighting. They also cover things like traffic signals and reflective devices. The SAE, Society of Automotive Engineers, has issued its SAE J578 standard, and this, among other things, specifies the allowable colors that can be used in automotive lighting applications. Of course, automotive is a worldwide business, and there's several countries have different regulations, and so there are committees that are working to harmonize the regulations across several countries, various countries, so that manufacturers can introduce the same vehicle with minimum changes required. A couple of standards that cover LEDs in particular from the SAE. The SAE J1889 first came out in 1988 and has been revised periodically since then. That one covers LED use in general, and SAE J2650, which dates back to 2005, applies specifically to LEDs used as illumination devices. In other words, LED headlamps. This particular standard covers LED-specific issues, such as the light degradation over the rated lifetime, as well as the minimum red LED color content, so that, for example, we can look at a red sign, like a red stop sign, and see it effectively. Because as you know, the red is reflection, and if the LED had no red content, then we wouldn't be able to see the red stop sign very effectively. A couple of other important regulations we'll talk about, which are not specifically related to LEDs, but nonetheless govern many aspects of LED design. The ISO 26262, the so-called functional safety standard. Functional safety is an important part of automotive design. It basically mandates that if anything fails, it will fail in a controlled manner, and manufacturers are now required to include a variety of fail-safe mechanisms, even down to within an IC itself. So something fails, it will degrade gracefully, as we say, and also there will be an alternate way for the driver to recover from some event, some failure event. Finally, AEC The Automotive Electronics Council, AEC, has issued the Q100, 101, and 102 standards, and these pertain to the manufacturing of integrated circuits and other components that are used in the automotive electronics industry. And what we find in the industry, Toyota, GM, Audi, and so on, and plus the Tier 1 OEMs may also add additional test requirements to their products in addition to satisfying these AEC specifications. Functional safety, since it's such a big part of automotive design, and since it's fairly new compared to many of the other things that we've been talking about, let's kind of review a little bit about functional safety. As I mentioned, functional safety is a methodology of ensuring that the equipment operates as advertised, and any failures can be recovered and are recoverable, I should say. As you can see here, the ISO 26262 covers a large number of devices. And essentially what they do is they classify events by severity, which goes, you see across in the columns of this table. S0 is an event that would occur, that the severity, there'll be no injury. And S3, conversely, if something happened there, that would be a life-threatening injury. And then exposure talks about how likely it is that such an event would occur. So, for example, E0 is incredibly unlikely, and E4 is something that might, in normal operation, have a higher probability of occurrence. And then finally, controllability says, well, okay, if this failure occurs, how easy is it to recover and control the vehicle in this situation? Again, C1, easily controllable, C3, difficult or impossible to control. And depending on where the particular failure falls in the list of possible events, we define an automotive safety integrity level, otherwise known as ASIL. This is a risk classification scheme defined by the ISO 26262 specification. And this is adaptation of standards that have been in place in other industries for many years. And so we define an ASIL going from no problem, and so we don't need to worry about it, all the way up to ASIL D, which is the highest degree of hazard and the highest degree of rigor that the automotive manufacturer must apply to the design. And so you're thinking, okay, well, what does this have to do with lighting? Because, you know, lighting, that's clearly, or maybe it's not, clearly not a safety-related issue. Well, the question is, yes, it does. This is a slide from TÜV, which is the German, one of the German safety organizations, analogous to UL in this country. And you see here that they have included several of the lighting functions in their ISO 26262 discussion. And it's particularly important because, as we'll see, lighting is now part of an integrated system design, which has lots of microcontrollers and software-intensive designs are very much part of the ISO 26262 standard. In addition, of course, things like adaptive front lighting are clearly things that, if they went wrong, could cause danger not only to the driver of the vehicle, but to oncoming drivers too. Let's talk a little bit about some key automotive lighting definitions. Lighting has some specialized definitions. Let's look at these. Luminous flux. This is, the unit is lumens, is a measure of the amount of energy per unit time that is radiated by a source, from a source. And this takes into account the response of the human eye, because the human eye, of course, does not respond equally to all wavelengths. Luminous efficiency, this is expressed in lumens per watt, is a measure of the ratio of visible light produced per the amount of power consumed. So this is the efficiency of the light source. And finally, color temperature, which is in Kelvin. It's a method of expressing the visible appearance of a light source in terms of its resemblance to a black body, which is a physics concept that we'll discuss in a little while. So what do we call color anyway? Well, color is, as you remember from your physics class, is a sensation resulting from a given spectral distribution of light. And of course, the eye has three different types of sensors, and they detect light in different measures, and the brain interprets it. And the sensors are called cones, which I'm sure we all remember from our biology class, and sensitive to red, green, and blue, respectively. And way back in the 1920s, there was a groundbreaking series of experiments that produced this diagram that's called the CIE chromaticity diagram. And CIE is a French word, and pardon my French, is the Commission Internationale de l'Éclairage, which is the International Communication on Illumination. And this diagram came out in 1931. And what it shows is the entire range of colors that can be perceived by the human eye expressed on a set of XY axes. We don't really have time to talk about this diagram here, but you can see the wavelengths around the outside expressed in nanometers of the various colors. So again, as we probably remember, an object appears white if it reflects or emits all visible wavelengths, more or less equally. There are different shades of white. If you're an interior designer, you'll be well aware of this. And differences in the distribution of frequencies result in subtle changes in how we perceive white. And so the SAE has developed an allowable range of color frequency combinations of red, green, and blue that qualifies as different colors. And you can see that here. These are the SAE definitions of white, red, yellow, green, and blue light. And for a headlight, for example, to qualify as white, it must be within the block labeled, not surprisingly, white on this diagram. The next thing that we've talked about in the last couple of slides is color temperature. And this gets back to this idea of a black body radiator. And in physics, a black body is an idealization. It's an object that absorbs all incident electromagnetic radiation, just like a black hole in science fiction, or actually science reality, corresponds to an object that absorbs all radiation too. So a black body, importantly, is also an ideal emitter at every frequency. And the color temperature of a white light source is defined in terms of its resemblance to a black body emitter at the same temperature. For example, the sun closely approximates black body radiator, and the color temperature of the sun above the atmosphere is about 5,900 K. Incandescent lamp is also a pretty good approximation at a lower temperature between 2,700 and 3,300 K. So let's take a look at what these look like in practice. You can see here that this is a comparison of color temperatures of different high-intensity discharge bulbs. And generally speaking, the lower temperatures tend towards the red end of the spectrum. And as we get higher temperature, we go through up to the blue end of the spectrum. So you can see here that the yellow appears as a 3,000 K color temperature, and then going all the way through, and we finally have blue through to purple, getting up to 12,000 K. And so that's how we define the output of the lights that we're going to be talking about next. So in the next section, let's take a look at some of the lighting technologies that are currently in use. The earliest that came out after we got rid of candles and acetylene lamps was the incandescent bulb. And an incandescent bulb uses a tungsten filament in inert gas or vacuum atmosphere, and luminous efficacy is about 16 lumens per watt, operating for about 1,000 hours, and that color temperature is about 2,800 K. That was the only game in town for about 50 years, and then more efficient technologies came along, starting with application in headlamps. Now they're pretty much obsolete for headlamps and are slowly being phased out in other applications too. Compared to some of the other technologies that we'll be talking about, they're very inefficient, they have short operating life, but they're very cheap to manufacture. And I'm sure that we all know that incandescent lamps are being phased out in other areas of our lives too, notably in the home, and first of all, complex fluorescence, and then coming along with LED lamps also. And consequently, legislation is appearing in many countries that is slowly phasing these out. So around about 1960, we saw the next revolution or advance in light technology with the introduction of the halogen incandescent lamp. Very similar in operation to the original incandescent bulb, but it adds a halogen such as iodine or bromine to the inert gas. And the combination of the inert gas, the halogen gas, and the tungsten filament produces a chemical reaction called the halogen cycle reaction, which increases the life of the filament because it redeposits tungsten that would otherwise evaporate back onto the filament. And therefore, the lamp can be operated at a higher temperature than a standard incandescent bulb, and produces light of a higher color temperature. In other words, 4,000 K versus 2,800 K. And these have been used for many years, and now they are giving way to the next technology, which is high-intensity discharge, or xenon. This uses a different technology. This uses an electric arc to produce light, and it's more efficient than lamps based around tungsten filaments. We have them in a range of color temperatures. They're about twice as bright as halogen lamps, which has an advantage in that it helps drivers react quickly to driving conditions. But that also gives rise to a problem because it could potentially cause glare in oncoming drivers. So, for example, regulations in Europe require headlamp leveling systems in vehicles with HID. They're also more expensive to produce and install, repair, and so on. But that's partially offset, as I said, because they have a longer life, which is twice the length of time of some of the other technologies we talked about. The first HID lamps that came out contain mercury, which of course is a toxic heavy metal, and the disposal of that is very highly regulated. But more recent designs have removed this ingredient. Which brings us up to the current state of the art, which is LED lighting. And this is a semiconductor. As we know, LED has been used for many years as indicators and in a wide range of electronic equipment. They produce light via electron and hole recombination, And they've been used for over 10 years in some automotive applications, such as taillights and turn signals. But now, as the brightness is improved and the power output is improved, they are now starting to be seen in headlamps also. Right now, it takes an array of LEDs. You can see here, this device has multiple LEDs to produce enough illumination for a headlamp, but there are single LEDs with up to 1400 lumens exist. And as we'll see later, tomorrow, in fact, the higher, the latest LEDs can actually produce high beam and other LED lights outputs in the using multiple LEDs optimized for different applications. The great thing about LEDs, although they are more expensive to produce, and certainly for the drive circuit, they have an operating life that dwarfs those of the others, 50,000 hours in this case. As a result, they are increasingly replacing other technologies, and this technology is what we will be spending most of our time talking about in the balance of this course. So if we start looking at these technologies and comparing them, this is how they stack up. As I said, you can see that incandescent lights are the cheapest to manufacture, but lowest efficiency. Conversely, LEDs are the most expensive, but have tremendous advantages in terms of operating life and light output efficiency. You can also see that the color temperature for LEDs is as good as HIDs. In fact, LEDs can be made, as we all know, with a range of colors. First ones that came out were red and green, and then white LEDs and blue LEDs followed along later. And then at the bottom, we have the relative cost from cheapest incandescent to LEDs at the most expensive. So let's just talk a little bit about the why LEDs are a better choice. The first thing that we should mention is that LEDs turn on much quicker than other technologies. Incandescent bulbs, as we all know, take some time to heat up to temperature to emit light, but LEDs turn on a lot quicker, which can actually result in saving lives, because a quicker turn-on time gives drivers a greater amount of time to react to oncoming brake lights, or the guy in front brakes. You have that extra few milliseconds to respond, and this can translate into real reductions. So the example here is at 100 kilometers an hour, which is 62 miles an hour. That can give you a 5-meter reduction in stopping distance. The extra short amount of time you have before you notice that the guy in front braked. Result is a reduction in rear-end collisions, and this is, clearly as cars become congested, the traffic conditions become more congested. We have more vehicles on the road traveling at higher speeds, and that can translate into lives saved and potentially even insurance premium reductions. And perhaps this is one reason why the German manufacturers have led in this area, with the Autobahn's high operating speeds. The next thing is energy savings. You can see here, this is a comparison of the energy savings from LEDs compared to a mixture of halogen, and incandescent lamps. You see here the energy savings are up to 60%, and the rest of this diagram indicates where the savings are to be found. This is rather difficult to read, but in Europe particularly, the authorities have developed goals backed up by regulations for the amount of CO2 emissions that can be produced by cars. And you can see here that the LED lights can save per 100 kilometers up to 0.12 kilograms of CO2 emissions versus the other options, even using a mixture of xenon and LEDs there. And the decrease is 60% relative to conventional lighting and 39% relative to xenon and LED lights. So this is a big deal, and of course, this is one of those things where we can expect over the next 5 or 10 years that consecutively more rigorous standards will be introduced by authorities. And of course, the European Union is not the only country that's doing this. The United States is following suit, and also in the Far East. So we can see that LEDs, there's an advantage to the manufacturers versus using other, as if they needed any other reason to change. This in itself will mandate be a market driver in terms of introducing products in the marketplace. Well, this was a short presentation, mostly because the way that the course breaks out, this was a relatively concise part. So right now, this was part one, concluded for the presentation. So I thank you for watching, and now we'll see if we have any questions that have come in from our audience.
Great, thanks, Paul. Patrick here again. So now we move on to the next stage of our presentation, which is the Q&A section. And as a reminder, to participate in the Q&A, just type your question into the text box located to the right of the presentation window, or click the Q&A icon on the bottom of your screen, and then click the Submit button. We do have a couple of questions coming in, Paul, so if you're ready, take a break, have a glass of water, and we'll jump right into it. You ready?
Yes, I'm well hydrated,
okay.
Thank you.
So the cost of LEDs, we have one coming in from John. The cost of LEDs has been prohibitively high over the years. Is that cost coming down? Are they coming more in line with the cost of what would be, I guess, traditional LED or traditional automotive lighting systems?
I wouldn't say it's competitive, but certainly the cost is coming down. Cost is one of those things that's heavily dependent on volumes, and at least for semiconductors. As we'll see in subsequent days, there's a lot more to driving an LED than just flipping a switch which connects the battery to the lamp, which is what it used to be for many years. And there are multiple elements of cost and multiple things that you need to consider when driving an LED, but certainly the cost of the main device is definitely coming down. And I think what's just as important is that manufacturers are now thinking of a lot of innovative ways to use an LED light, which new aspects that they couldn't do with regular incandescent lamps. I mean, so we have, we'll see the so-called organic LEDs, which we'll talk about tomorrow, I believe, allow all kinds of different colors to be done. And of course, the volumes, as they're becoming prevalent in more and more applications, the volumes are going up dramatically, which drives it down the cost curve. I mean, we're all familiar with the cost of pretty much any other semiconductor, following the famous Moore's law. I mean, they've all been coming down for year on year. almost regular as clockwork for decades, and we expect LEDs to follow the same path. So I would still, yes, they're still more expensive. It's a multifaceted question. It involves both the LEDs and the driver circuits. Consequently, they're slowly starting at the high end of the market, Mercedes, Audi, Rolls-Royce, and so on, and then migrating down commensurate with as the cost direction comes down.
With OLEDs, are they becoming part of the in-cabin LED lighting, or are they external?
No, they're very big. In fact, the last thing, the final frontier, if you will, is headlights. Started out, as I said earlier, with the external rear lights, and then internal. And that's, as we'll see tomorrow, that's not only what they call mood lighting, and it's also instrument panels and instrument clusters and displays and so on and so forth. We're not really going to talk much about backlighting. That's a completely different topic, you know, as you see in the TV. But yes, they are pretty much everywhere in the vehicle now where lights are needed. And they're given free rein to designers to be more. I'm sorry, what was that?
I think just go back to the cost factor, I guess, right? We'll discuss more of the costs and the semiconductors themselves in the next couple of days, right? Day 2 and day 3.
Yes, yeah, the cost factor. I mean, interior lights are much lower power, so the cost is not so much of an issue, and you don't have to come out with complicated heat sinking requirements. But what it's done is given free rein to the stylists in the vehicle, who now can, you know, let their imaginations run wild, if you will, when it comes to, and we'll see some pictures of that, some examples over the next couple of days.
I've got a question here from Fausto. What's behind the use of DC to DCs for LEDs? Why are we using DC?
Well, an LED
voltage management, right?
Well, yeah, an LED is a current control device, and we need to essentially we need to control current through it. And as we'll see, there are several ways to control an LED. The simplest way is just with a resistor in line, and but more sophisticated controls, especially when we start talking about dimming, things like this, we need a much more semiconductor intensive way of controlling them, DC to DC. Again, this is something for day 3. We'll discuss the various uses of various LED drive circuits and talk about their advantages and disadvantages for this particular application.
Is there any new regulation? This has come Jiang. Forgive me if I got your name pronounced wrong, but is there any new regulation on the LED market for automotive lighting in the USA? Any new rules coming down, especially as the market takes off, I guess, right? Any new regulations that you know of that are happening?
Not that I know of. I mean, the functional safety one is that people are still trying to work through that. What is, in fact, the standard ASIL level B is what people are starting to put the functional, the category of functional safety that people are starting to assign to lights. Which of course it's not as bad as, you know, steering controls, for example, but still it does require a level of testing and design to mitigate against failures. And that, I think, something is people are still figuring out and introducing new products with taking this into account. But of course, functional safety affects pretty much every part of automotive design these days. And even we did a presentation a few weeks ago where we talked about power distribution network, and that again is covered by functional safety. I don't know about any specific LED requirements. I think most of the standards have been well defined, and I'm sure they're working on revisions. I mean, these standards are updated every few years now, and I don't know of any brand new standards. There are already standards, as I mentioned, that pertain to LED lighting, both headlamps and other lights that have been issued.
What are some of the ways in which functional safety can be addressed with LED lighting, right? I mean, redundancy is kind of difficult to do, right, because of space, right? So you need to, is it guaranteeing a certain level of lighting?
Yeah. If we look at a modern state-of-the-art automotive headlight, you will find that there are multiple different LEDs for different functions. And so that provides built-in redundancy. So, for example, if your high beam headlight LEDs fail, you can automatically switch to a low beam LED headlight while alerting the driver. Another way might be to have redundancy in the driver circuit. There are various aspects. I mean, if you look at the whole signal chain from the switch or the sensor, in fact, we're not even talking about switches now, we're talking about sensors and cameras that detect, for instance, oncoming drivers. There's a complicated signal chain that goes from that through the microcontroller to the driver circuit. And every aspect, each part of the chain has to be designed so that if a failure, in other words, a single point failure, should not cause your lighting to go away. Automotive manufacturers or OEMs need to design various aspects of the system to detect these things, perform diagnostics, alert the driver, and also switch power so that the fundamental function does not just go away. So it's a multifaceted question. As I say, manufacturers are still trying to work their way through these.
We have a question coming in from Julio Costa. Is DRL expected to be regulated in the U.S.?
Is what?
DRL. I'm not sure what DRL is referring to. Julio, can you send that question again? Find DRL. Interesting. In the meantime, I have a second question from Saravana Kumar. Do we need to consider LED life for mean time between failure calculations? Yes, we would, right? But functional safety in particular.
Well, as part of a system.
Yeah.
I mean, yes. And of course, the LEDs themselves in the qualifications for mean time between failures, I'm not an expert in this area, but the manufacturers will look, if you look at the specifications for an LED, there will be a fairly comprehensive series of charts and specifications dealing with the failures to be expected at certain points in the life. So after 1,000, it's a 50,000 hour life, and we guarantee that no more than 1% will fail after 1,000, and no more. I mean, there's a curve. So certainly, I mean, in the sense that it's an automotive device, has to meet these requirements. I think AEC Q100 and similar specifications do all actually have reliability goals. And as I said, the manufacturers themselves issue their own standards. It should all be in the data sheet, and then there'll be a qualification program for LEDs that will tell you the reliability testing and so on that the manufacturer carries out for automotive qualified parts.
Yeah. I think there's a second aspect to that, Paul, in the sense that LEDs in most cases won't fail directly, but they will dim over time, right? So are we seeing more incorporation of feedback mechanisms to either boost the LED output as the luminosity decreases over time, or the luminous intensity decreases over time as they fade a little bit, or wear out?
There are two ways to look at this. I mean, you can, if it's, first of all, yes, you're right, it does degrade over time. That would mean that the manufacturer can either detect, there are ways of detecting this, can detect the failure and alert the driver to say, hey, this has reached the point where with a suitable safety margin, time to replace the LEDs. And secondly, as I said, they could, while still alerting the driver, they could switch operation to another LED or use one of the other LEDs in the LED matrix to make up for that lack of light.
Or could they drive it with more current? Increase the current output, or increase the drive current to that LED.
They could increase the current output. The problem with increasing the current output is you increase the temperature, and as we'll see later on, that the failure rate of LEDs increases tremendously as the temperature goes outside. It's the maximum. So, but yes, I suppose you could do that.
A little bit, I guess. Maybe do a little bit of compensation, but you can't do too much of thermal reasons.
Yeah.
Okay.
I think that would be a pretty slippery slope. Those types of things beyond a relatively small amount
window, I guess.
Yeah.
Okay.
Yeah.
Julio clarified. Thanks, Julio, for doing that. He's referring to, of course, the daylight running lights. It's regulated in Europe, but not in NAFTA. That we've seen anyway. So, are you aware of any regulation around daytime running lights in, I guess, here in NAFTA or in the US?
You mean specific to LEDs? No. I mean, I think to the extent that they have regulations for any type of daytime running lights, I'm not aware of anything specifically to do with LEDs. But of course, LEDs must conform to whatever standards we have in place anyway for daytime running lights. But not specifically for LEDs.
Yeah. Okay. Actually, I do want to come back to that in a second when you consider efficiency for electric vehicles and the importance of LEDs. But Magdalena has a quick question from Brazil about the alternative to LED bulbs. Is it possible to substitute the halogen bulb if we do the right optical reflector specific to that bulb?
You mean just a straight switch? No.
Yeah.
No, I mean, these are typically not. And in fact, there's a lot more to it than just, especially in state-of-the-art headlights, there's a lot more to it than just swapping it out. Because, I mean, these LEDs, again, as we'll see tomorrow, these state-of-the-art LED headlights have multiple LEDs, which with beam forming. So, for example, you'll have an LED LED headlamp assembly that, for example, illuminates everything around an oncoming vehicle, but not the oncoming vehicle itself, to avoid glare. So, I mean, those types of things need a tremendous amount of controllability in the LED and steering of the beam, and it's really not a question of just swapping them in and out. I mean, you can't even swap in and out non-LED lamps. I mean, you can't take an HID light and just slot it in place for halogen, for example, because I mean they have different drive circuits and so on. So no, it's becoming more specialized, and of course that also raises the level of diagnostic and technical ability required of everybody in the process, including the repair mechanic. So.
I used to be able to take out the bulbs and replace them myself, and now I have to replace the whole.
Well, yeah.
Right?
I mean,
you got to change the whole assembly, right? Yeah, that just happens.
Exactly. Yeah. It's
too complicated.
So you're talking about electric vehicles, right?
I think. We got a question about that, right? Because the importance of LEDs for EVs is rising, right? You've seen reports recently about the industry turning almost entirely to EVs, right? Switching to EVs instead of hybrids.
Yeah, so, it's a long, slow ramp, but yes, they are, and of course, LEDs consume less current to produce because they're essentially more efficient than other methods of producing light, and so therefore, in terms of electric vehicle, that leads directly into increased range for the battery. So if you have less strain on the battery because you have LED lighting versus incandescent, then you're going to have increased range. And range anxiety, it turns out, is one of the most the reasons most given by people for not buying certainly a pure electric vehicle, because they're afraid they'll be stranded somewhere.
Sure, yeah.
And, they'll basically, especially given the lack of charging stations now in the current infrastructure, it's very difficult to recharge your electric vehicle when you need it. And so anything that will help mitigate that range anxiety, which would include LED lighting, and of course, is a good thing. And of course, manufacturers are well aware of this, and they are designing, right from the get-go, they're designing these types of things, LED lighting and similar technologies into the vehicles. So the whole vehicle system design is predicated with a view to maximizing the range of the battery. And clearly, there are two ways to accomplish that. There's making batteries better, and there's reducing the drain on the batteries we have. So it's a double-sided coin.
Yeah, batteries tend to be what they are, right? I mean, they aren't changing too quickly. But I guess on the topic of daytime running lights, right, if that becomes regulated or mandatory here in the US, which I'm not sure it is, right? But if DRLs are mandatory, then it's
I'm sure daytime running lights are.
Yeah.
But LED specifically in that application, I'm not sure is regulated.
Right.
I mean, other than the daytime running lights.
That's going that'd be a huge drain on the batteries if whether it's regular lighting or LEDs, right? So you have to switch to some
but even there,
options.
Right, exactly.
Richard Nakeo from Nakeo International. What's the next goal of color temperature for white light, which is 12,000 Kelvin, right? Currently say it's 4,000 Kelvin. Is 10,000 achievable or over? I guess that's what
the color temperature, more is not better. I mean, if you carry on increasing the color temperature, you end up, as we can see from one of the slides, it goes through white and then into blue and so on. So, I mean, the answer is, in terms of the semiconductor technology, clearly yes, because I mean we have LEDs that run the gamut all the way down to infrared right now. So. I think
the question is really about aesthetics, right? You want the
aesthetics, and there are other things like what is the efficiency of that of different LEDs, the different colors, how expensive would it be, and what would you gain? I think there's probably we'd probably find that there is an optimum illumination value, if you will, for an LED. Of a certain color, and that's beyond that. Once we settle on that, or once we've determined that, then the next thing would be to increase efficiency of the underlying system. In other words, let's say if 12,000 was 12,000 actually was at the ultraviolet end of the spectrum, as we saw in slide number 12. And so if that was determined, it seems like 10,000 might be a better one, but still, then it would be the question is, okay, we determined this, and now we need to drive the efficiency high, up as much as possible to reduce the drain on the battery or the load on the engine.
Richard, I guess we'd be curious as to what kind of applications you'd be looking for that, right? So if you can send a quick note on that while we're still here.
I mean, certainly, if you look at the allowable colors for the SAE specification, you'll see that white is within a certain area. I mean, it's not like you can just arbitrarily put in a color and say, if it doesn't meet the SAE specifications, then it doesn't qualify as a white LED. And so I think there are good reasons why it's within this fairly limited area of the CIE chromaticity diagram that we saw earlier.
Okay. Just a heads up for the audience, we're wrapping up shortly, but if you have any last minute questions, please send them in now. I've got one more to get to here, Paul. I guess it has to do with temperature range, right, and temperature tolerance for LEDs, right? One of Tony here mentions that he's got one of his customers are in the Middle East, and he's concerned about LED handling heat well, temperatures, high temperatures. But I guess better than HIDs or halogens. Do LEDs handle high temperature extremes better?
Well, in a vehicle, of course, automobile manufacturers must develop their cars for different temperatures. I mean, when I was working at General Motors, we used to go up to Northern Ontario during the winter for the cold start testing, and then we used to go to Death Valley in the middle of summer for the hot weather testing. And the vehicle must, survive all of those. And some countries may or may not allow LED lights for various reasons. I know if you look at a lot of the state-of-the-art LEDs now, you'll see a lot of attention is paid to cooling. Turns out that LEDs, although if you touch an LED lamp, it appears cool, the heat goes through the leads of the LED down at the printed circuit board, so that gets extremely hot. And so manufacturers are well aware of the heat distribution, the thermal management issues with LEDs, and so what they do is introduce cooling, whether that be large heat sinks, large PC board areas, or in fact even cooling fans. So, I mean, and these decisions are all made by the manufacturer, not necessarily, by third parties. So I assume that anything that's sold in the Middle East will either not have LED lighting, if that would be a problem, certainly for headlights, which is really what we're talking about, because that's the most power distribution, the power-hungry application. They may not have it, or if they do, then it will be well characterized,
managed,
and were designed to accommodate that environment.
Okay, I think it's our time to wrap up, Paul. So to our audience, any last-minute comments before we sign off, Paul?
No, I hope everyone will tune in tomorrow, and we'll discuss more detail about LED architectures and some of the applications for LEDs, and specifically, and then day 3, as I said, we will be talking specifically about some of the design questions that we alluded to today, and we had some questions about. So I look forward to seeing everybody tomorrow.
All right, sounds good. And just a quick note for our audience, and if you didn't sign up for parts 2 or 3, you can find the link in the green resource folder to register. And for more information related to today's webinar, visit any of the resource links available in the green folder icon at the bottom of the screen. And of course, within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. You can go back over it again. So thank you again for attending part 1 of this week's course, Introduction to Automotive Lighting, brought to you by EETimes and Semiconductor. The webinar is copyright of AspenCore 2019, and the presentation materials are owned by or copyrighted by EETimes. And of course, the individual speaker is responsible for his content and opinions. On behalf of our guest, Paul Pickering, and on Semiconductor, I'm Patrick Mannion. Thank you, and be sure to join us tomorrow for part 2, selecting and using the right LED technology. Thanks for joining us. Have a good day.